Hey Jacob. Hey Psych. Hey Charles. Hey Justin, get out of my way!
Momentum. Hello? I am the narrator and I will be in the background explaining the flaws in physics of our boy Ryan Y-E-N. Right here we have an example of momentum. Momentum is the quantity of motion of a moving body. You can find the momentum of the basketball using the following formula. P represents momentum and is expressed in kg times m over s, or kilograms multiplied by meters per second. Using the formula, we know that to find the momentum of the basketball, one can simply multiply its mass by its velocity. If the basketball had a mass of 2 kilograms and was soaring at a solid 5 meters per second, the momentum of the basketball would be 10 kg times meters per second. This was found by plugging 2 kilograms and multiplying it with the 5 meters per second.
Dude, why are you so bad? Speed was like 21-0.
Yo, what do you mean, man? You microwave head. I'm going home.
Oh my god, did you see that guy? He's so trash.
What do you expect? When has Ryan ever been good at anything?
Hey, man. I don't like what you have been talking about me lately.
Man, just trash, snowman.
Hey, what the heck? What do you mean? Here comes momentum.
Let us examine the gnarly tackle by R-Dog. Right here we have an example of an inelastic collision. An inelastic collision is a type of collision in a straight line where two objects collide and stick together. This is the formula. It is important to note that A and B are two separate objects or beings. In this case, Ryan Y-E-N and Jacob are A and B. Numbers. Let's say that Ryan's mass is 75 kilograms while Jacob's is 50 kilograms. Since Jacob was standing relatively still before the collision, we'll let his initial velocity be 0 meters per second. And we'll say that Ryan is in exactly Usain Bolt and is running at 2.0 meters per second. What could possibly be their final velocity? Well, if we put the numbers into the formula, it'll look a little something like this. Firstly, let's multiply the kgs by the m over s's. Finally, let's divide both sides by 125 kilograms to isolate the final velocity of the two. By plugging it into the calculator, we can see that the final velocity of the two boys is 1.2 meters per second.
Oh my god. Oh my god.
Sorry, Jacob. Sorry.
Oh
Sorry,
my
man.
Oh.
Ha! Psych! That's what you get, you zucchini head. Hey, Charles, let's go play pool.
Okay, let's go play ball.
Charles, are you ready to go?
Yes, sure.
Let's go.
Let us examine the preposterous purple pool balls. This example of the pool balls shows the idea of conservation of momentum, and how momentum is always conserved, even after the collision. In other words, the momentum of the two objects before the collision is equivalent to the momentum of the two objects after the collision. You can find the mass or velocity of the two objects using the following formula. In this case, the cue ball and pool ball are A and B. If the pool balls have the same mass of 1 kg, and, in an ideal world the objects were frictionless, the cue ball's initial speed should be equivalent to the pool ball's final speed. If the cue ball was moving at 5 meters per second before the collision, the pool ball should move at 5 meters per second after the collision. Now for some proofs. Conservation of momentum formula. Let's plug the numbers into the formula. Let's multiply everything out. Now let's divide both sides by 1 kg to isolate the final velocity of the pool ball. The pool ball's final velocity is in fact 5 meters per second, same as the cue ball's initial velocity.
Maybe you should go back to swimming, because this definitely isn't right pool for you.
What? You're not supposed to talk to me like that.
Okay, I'm just trying to help you, you know.
What? Yo, screw you. Here comes momentum. That's what you get, you nasty lemonberry. Hey man, you wanna go play some ping pong? I have been having a bad day with sports.
But I don't even know how to play pong.
Yeah, whatever, let's go.
I'm back. This time we're examining impulse. Impulse is the change in momentum, while F is the average force acting during the time interval over which force was applied. The formula for impulse is as follows. Impulse can also be shown as such. Now, impulse is still a form of momentum, so the formula could be written as such. I say as such a lot. With this knowledge, let us examine the impulse exerted onto the ping pong ball from the racket. Time to make up some more numbers. We're going to pretend that the average force of the racket striking the ping pong ball is 25 newtons over a time of 10 milliseconds, also known as 0.010 seconds. The ping pong ball has a mass of 0.0030 kg. Let's also pretend that we managed to perfectly hit the ping pong ball at its highest point in the air, leaving it at an initial velocity of 0 meters per second. What speed will it have after impact? Let's plug in the first formula to find the change of momentum, or the impulse. Multiplying it out gives us a pretty radical change in momentum of 0.25 newtons times seconds. But we're not done yet. The question was asking for its final speed. Let's plug in the numbers for the ping pong ball because we know its mass and initial velocity. Now let's plug in the numbers for the change in momentum calculated from earlier and simplify the right side as well. We can write the change in momentum in units of kilograms times velocity. And now let's divide both sides by 0.0030 kilograms to isolate its final velocity. We find that the ping pong ball's final velocity is 83 meters per second. Alright, we're on the last one, folks. Elastic collisions. The difference between elastic and inelastic is that objects stick together in inelastic collisions, whereas they collide and go off separately in elastic collisions. Luckily for the basketball, it didn't have to stick onto Ryan YEN like poor Jacob did. The formula is as follows. It's like the same thing with conservation of momentum, except left and right side have switched, so it's like the same thing. Now Ryan's mass is still 75 kilograms and the basketball is still 2.0 kilograms. If Ryan was walking in at 1.5 meters per second and the ball was thrown at 7.0 meters per second in the opposite direction, what would be the ball's final velocity if Ryan fell backwards after the collision at 0.1 meters per second? Let's plug in them numbers. Multiple multiplications occur. Simple subtraction simulator. Attractive addition analyzed. Divine division deluxe. Answer required 53 meters per second. Keep in mind we made all of these numbers up. Is he dead?
I don't know.
This sucks, he was such a nice guy.
Yeah.